Welcome to the 55th lecture in this series. So let's continue our discussion of the wedge product. Last time we constructed a special corresponding to each multi-index. We constructed a K form. Multi-index of length K will give rise to a K form. And of course, as usual, we have a fixed basis for one forms in the background. So with that basis and a multi-index, I come up with this epsilon I. And the claim is that now, I'm going to restrict to multi-indices where all the entries are ordered. They have to be in a strictly increasing fashion. And if I confine myself to such multi-indices and look at the corresponding K forms, that forms a basis of AKV, and that immediately gives us the dimension of AKV to be n choose K, n factorial by K factorial times n minus K factorial. So I was in the process of proving that these special K forms actually span AKV. So I started with an arbitrary K form and I came up with these numbers where I just evaluate, which are obtained by just evaluating the K form on EI1, EIK for a multi-index I. Again, multi-index of that type, strictly increasing. With these numbers, the claim is that alpha equal to alpha I epsilon I, and the reason why this is the case is well, if you want to see this is true, as we have seen many times, in order to check the two K tensors are equal, we just have to evaluate both tensors on basis vectors by multilinearity, and that's what we'll do. Well, so we just have to check that alpha and alpha and the right hand side are equal when evaluated on, oops, here I should, there's a small typo, let me correct this, EIK. So I just have to check that these things, both sides are the same, give me the same number when evaluated on basis vectors. So let's do that. In fact, what I claim is that that's what I said is true for any tensor, K tensor, but when you have an alternating tensor, it's enough to evaluate them not just on any basis vectors, on a sequence of finite sequence of basis vectors, where with this property that the indices are increasing. We note that, let me write it as a small fact, we note that if alpha and beta are in AKV and alpha EI1 EIK equal to beta, oops, here it should be I1, beta EI1 EIK for all I1 less than I2 less than IK, then alpha V1 Vk equal to beta V1 Vk, i.e. alpha equal to beta. So again, this is something which follows immediately from the definition of an alternating form. So first of all, one notices that if any two indices I1, IP and IR are the same, then both sides will be 0 by the alternating property. So one can assume that I1 up to IK, they are all distinct. And if they are not in increasing order, you can interchange, keep on interchanging the indices so that they get into an increasing order. And the number of, each time you do an interchange, you will acquire a minus sign, but that minus sign will occur for both left hand side here and the right hand side here. So ultimately you can cancel the, so you can cancel the negative sign, and you keep on doing it till you put them in an increasing order. So that this property, we can assume this. So it's enough to check for sequence of basis vectors with this indices ordered like this. And when I have such a index sequence, let's start with something like that. Let J equal to J1 JK with J1 less than JK, as usual, as will be the case for everything that we work with. So then alpha EJ1 alpha EJK equal to I epsilon I EJ1 EJK, and this is the same as alpha I, and we have seen already the proposition, the small lemma that we had here tells us that this is the same as delta, the multi-index Kronecker symbol Ij. Now this delta Ij will be 0 unless I is a permutation of J or the other way around. But since they are increasing, the I and J are both increasing indices, to say that one is a permutation of the other, the only possible permutation which will keep the increasing property is the identity. So a term in the sum is non-zero if and only if I equal to J. So the permutation involved will have to be just the identity permutation. So in which case, therefore, the right hand side RHS equal to alpha J, and the left hand side equal to alpha J by definition. So both sides are equal, and this is true for any J, of course J with this increasing property. So we are done. So the two forms, so these forms will span the space of all K linear forms. Now as for linear independence, it's pretty much the same argument. So what we have shown is that epsilon I spans AKV. As for linear independence, suppose you start with a linear combination of this epsilon I. Now there will be some coefficients involved here, which I'll call it again by multi-index Ci, summation over all I. This equal to 0. I would like to prove that all the Ci are 0. We do the same thing that we did here. evaluate on ej1 ejk, j1 less than jk. Let's call this as multi-index j. If I evaluate on this, then the same logic gives us this is delta ij equal to 0, which implies the only term which will survive is when I equal to j. So I'll get Cj equal to 0. So in other words, for any multi-index with j1 less than jk, I get the corresponding coefficient to be 0. So therefore all these Ci's are all 0. And we have proved that they are linearly independent. Right. Now let's move on to somewhat slightly more involved lemma. The statement is simple enough, and this will be the crucial ingredient which will help us prove the associativity property. So the lemma states that, so let's start with K and L. So I length K, J is a multi-index of length L. So I want to claim that. So this is, I'll write the lemma below this. Epsilon I wedge epsilon K epsilon J equals epsilon ij, where ij is the multi-index which is obtained by concatenating I and j. In other words, you just write it as so if I equal to I1 all the way up to Ik and j equals j1 up to jl. So you just write it side by side. So I'll I1 Ik j1 jl. Now here I have to mention that the property, see, even if I had been written in an increasing order and likewise j, obviously that property might be destroyed when I do the concatenation. So that's one thing to observe. The other thing is that this, what we are trying to prove here, why do we even need a proof? It's just that the way we have defined this epsilon is in terms of determinants, not wedge products. The whole point is that this crucially links the wedge product with this, the determinant operation, and therefore it does require some proof. Now, right, so as I was saying, this remark Ij need not have entries in increasing order. So for example, if I take, so let's take n equals 4, and if I take I equals 1, 3, and j equals 2, 4, then ij would be 1, 3, 2, 4. So one has to keep this in mind. And now, okay, so let's prove this, and we'll look at, so we want to, as usual, see this is a k plus, both sides in this lemma are k plus L forms. It's enough to evaluate this on k plus L basis vectors, see that we get the same thing on both sides. So enough to check values on when both sides are evaluated on E1 all the way up to, rather not E1, EP1 P1 EP k plus L. But of course I can assume that these P1 all the way up to Pk plus L, they are in an increasing order, since that's the comment that we made last time in the previous statement, that if we have any two k forms and if you want to check that they are the same, it's enough to evaluate them on k basis vectors where the indices can be assumed to be increasing. So same thing here as well. So I'm checking that these two forms are the same, so I can assume that the P1 less than P2, etc. So P1 less than Pk plus L. Okay, so now let's look at some the possibilities. First of all, P contains an index. So the first possibility is P contains an index, an entry or an index, not an I or j. So remember that I and certain entry, so we are saying that this one of these, so let me write that again, I equals I1, Ik, j equals j1, jl. So one of these PR, let's say, will not occur either in I or j. If that happens, then this side epsilon ij will be, then the right hand side will be 0 just by definition. Then epsilon ij evaluated on EP1, EP plus k plus L equal to 0, because well, this is just the determinant of the one forms coming from I and one forms coming from j, evaluated on these vectors, and since we are working with dual basis, one gets this immediately. So this is by definition of epsilon I j. That's the right hand side. Now what about the left hand side? Well, the left hand side is a wedge product. Similarly, left hand side, the LHS equal to 0 since each term in the expansion defining the wedge product will be 0. So I'm looking at this EP1 etc. EP plus L. This will be, now this will have the wedge product is by definition you will be looking at things like this: epsilon I tensor epsilon j evaluated on E sigma P1 E sigma P K plus L actually no, I should write it rather like this. So not what one is permuting is E P sigma 1 E P sigma K plus L. This will be a typical, then there's of course sine sigma. So the expansion will consist of, will have terms of this form, and the tensor product by definition, this will be epsilon I acting on E P sigma 1 all the way up to E sigma P K multiplied by epsilon j sigma K plus 1 P sigma K plus L. Now the point is that if this index set, if the numbers P1 up to Pk plus L had something which was not in I1 up to Ik or J1 up to Jl, even after you do permute them in any way, the new index set will also continue to have some number which doesn't occur as part of I or J. Therefore, that extra number which was in the index, which was an entry for P, will occur either amongst these or amongst these. So whenever that occurs in, then the corresponding epsilon I evaluated on that will be 0. Similarly, this epsilon I or epsilon j will be 0. One of these two terms will be 0, and therefore the whole sum is 0. So if this happens, then so one can assume that there are no terms which are not already in I or J. Case 2 is that, well, that still leaves us quite a few possibilities, namely they can actually involve permutations of the entries of I and j. But let's assume in fact that a simple case, namely P is actually equal to ij. Right. So P equals ij. In this case, so one is still interested, so let's evaluate the right hand side. Now if I evaluate on, so epsilon ij evaluated on EP1 all the way up to EPK plus L is the same thing as epsilon ij. So it's EI1, since this index set is a concatenation, EIK, then I'll start with EJ1, EJL. Now this is equal to 1 again by the definition. Go back to the determinant definition of the epsilon forms, and then immediately it's clear that this is equal to 1. What about the left hand side? The left hand side is what requires a bit of work. So let's look at the left hand side. This acting on EP1, EPK plus L is by definition this is K plus L factorial, K factorial, L factorial, alt of EI tensor EJ evaluated on EP1, EPK plus L. And alt already has a 1 over K plus N factorial, so 1 over this, and then use the definition of alt. So sigma belonging to SK plus L sine sigma. Then here I have epsilon I acting on EP sigma 1, EP sigma k multiplied by, so I've already used the definition of the tensor product when writing this step, multiplied by epsilon j EP sigma k plus 1 oops, I forgot the P. P sigma k plus 1, and then I have E, the last term, k plus L, brackets here and here. So again we notice that in this each term it's essentially a product of two things here. The only way this is non-zero is that this P sigma 1, P sigma k, etc. belong is just as a set, it should be the same as the entries of I. So in other words, the sigma 1 sigma k should be just permutations of by the way, so this by definition, since it's a concatenation, let's keep in mind that the entries of, so I should mention that P1 pk plus l, since we have assumed that p equals ij, this is the same as I1 ik j1 jl. So what I want to say here is that this p sigma 1 etc. p sigma k should be nothing but a permutation of I1 all the way up to ik. So we'll stop here and I'll complete the proof of this crucial step next time. Once we have this, everything else is more or less straightforward. Stop here. Bye.